No.
That's the day.
It's on the day.
Okay, so we were doing the February, what is today? 12th? Time varying systems. So time varying systems that we were doing. So you remember last time we discussed all those awesome K, KL type
Yes,
functions,
yes.
right? Everybody can categorize them, right? What is a K, KL, K infinity, and then gave definitions in terms of K and KL, right? Like if your if your solution of X can be given as a KL, right? Where if X of t can be shown to be less than equal to or equal to beta X of t0, right? T0 comma t minus t0, then we know that this is a uniformly asymptotically stable, right? So that's the kind of objective we have. So let's go further into theorems. So another lemma we will deal with is 4.3, I believe. Let a Lyapunov candidate T2Rn be continuous positive definite on D. Let BR be a set of D where R is greater than 0, then there exists alpha 1, alpha 2. Now we are kind of what the objective of this lemma is to connect your positive definite Lyapunov candidate functions to this class K infinity function. See how they are connected basically. That's the idea. Belongs to KR such that you should be able to write. So if you have a positive definite function, the whole idea is you can upper bound and lower bound them using these class K functions. Okay, that's the idea. Alpha 2 for all x belonging to BR, some ball, right, in a D. So you have a D and you have a ball BR. In this ball BR, you should be able to write a positive definite function, and you can upper bound and lower bound it using a class K function, right? So that's the lemma. And let me show, like if you see, and if V is radially unbounded, so if V is radially unbounded, then these are K infinities, like class K infinities. So basically your radial unboundedness is related to that. So one example, so what I'm saying is, for example, you know that our Lyapunov candidate function V is always positive except at the origin. So something like this, let's say I have something like this, right? So like cannot make, like at 0 it's 0, but otherwise it is kind of positive, right? But it is kind of wiggly here. So what I'm saying by these mean like alpha 1 and alpha 2, upper bound, lower bound, is like you can always come up with these functions, right? So like alpha, this will be your alpha 2 and this will be your alpha 1. So basically you can have alpha 1, you can lower and upper bound to give a uniformity, like if instead of using that, so this is the whole idea. If we have positive definite function, you can always upper bound and lower bound using. It might happen that if it is not time varying, then the upper bound and lower bound are same, because see, we are using less than equal to, so it might happen that all of them are equal and so one example will be something like this, x transpose px, right? V of x equals to this. I don't know if you remember from linear controls also. P is a positive definite symmetric matrix, right? So this case, this x transpose px is related like this: alpha p max into x second norm and lambda p min of x second norm. So for a positive definite matrix, I can write that the maximum eigenvalue multiplied by the second norm and the minimum eigenvalue are your alpha coefficients, your alpha 1 and alpha 2. You can, so if you have, as a positive definite matrix, you can get those alpha 1 and alpha 2. So these are upper bound and lower bounds of these values. You remember this?
Yeah.
Right? So you don't remember this. Maybe I might have gone, but so this is the property of your positive definite matrices, that they are upper and lower bounded. This multiplication here is upper bounded by this and lower bounded by this, and they satisfy class K properties, right? When x is 0, this is 0, and otherwise it is always positive. When x grows, it also grows. So this will be done by like your alpha max, alpha min.
And so you say P min and P max, those are the minimum and maximum like elements in P?
Eigenvalues.
Like eigenvalues, okay.
So these are lambda is the eigenvalue of P. Value of P. Okay. So that's the property of positive definite matrices, is that. Get it? Somehow? This will be used at several places to actually give you a bound on things. Okay, so that's the idea. Like that's how. It's not necessary that this will be the same. You don't have to always use it, but this is one example that if it's a positive definite matrix, the upper and lower bound are easily computed, and they are nothing but their second norm multiplied by their eigenvalues. Got it? And more will be clear from the examples, but let's. So let's give the main theorem here. Theorem 4.8, I believe. And it says, it's the main Lyapunov theorem. Theorem for time varying systems. Okay, and it says let V defined on 0 to infinity. Now we can choose candidate functions which are time varying as well, right? So be continuously differentiable, and so remember in our time varying system we were always choosing V of x, right? Here we can choose Vtx. The Lyapunov candidate function can also be time varying. Okay, all the properties are settled, it can still be time varying. So first continuously differentiable, and then you have properties like V of tx is upper bounded by some positive definite W1x and W2x. Okay, so that's one. So this is time varying, but you can upper bound it by use time not time varying Lyapunov candidate function, and lower bound it using again time invariant Lyapunov candidate function. Okay, so second. So you should always choose Lyapunov candidate functions like this. And then when a Lyapunov candidate function is time varying, how would you compute v dot? How did we, if it is Vx, how did we compute? We did del V by del X, right? First we take a partial of V, right? And then we take a time derivative, this with respect to time, so that was f of x, right? In this case, if you want to take a time derivative of this, you are saying first with respect to time, because it's a function of time, so del V by del t plus del V by del x transpose of f into tx. That's your v dot, right? That's your v dot. Should be less than equal to some positive definite function or negative definite. This is positive definite, but after multiplying it becomes. So these where, so now we are adding these two additional constraints, that now your v dot will look like this, and if it is less than a negative definite function, less than a negative definite function, so we have to show that there will be some W3. Okay, and these are all to make sure, because once you add these things, the uniform definitions comes in, it becomes time independent, right? So that is the idea. When we are saying it, we could have always said, hey, it is less than 0, right? No, it is, to make it time independent, we are saying it is less than a negative definite function. So that's the whole idea, bringing that uniform asymptotic stability. So when W1, W2, W3 are continuous positive definite functions, then x equals to 0 is uniformly asymptotically stable. Okay, so note these W1, W2, W3 are time invariant functions, right? Remember that. Is the more, and because they are time invariant, we can say that uniform stability property from there. It doesn't matter what time you start, you are always less than that. So I won't prove it for the sake of killing you guys, but proof seems interesting. It's in the notes also, in the book also. But let's take an example first. I'm saying that if your v dot, which is time varying, is less than minus W3x, and W3x has to be a positive definite function, time invariant positive definite function. What is our WT here? Again, I have to first show that there is a lower and upper bound. It is lower and upper bounded by a positive definite matrices, or positive definite functions, not matrices. Definite works, right? So is there an example somewhere here? Okay, example. Let's say my x of x dot equals to minus 1 plus gt of x cube, right? So this is a time varying function, right? Gt is there, so g is continuous, and g is continuous, and gt is greater than equal to 0 for all t. Okay, that's what is known, like gt is always positive or equal to 0. So let's start with v of x. So it's not necessary that your v will always be time varying. If you can get away with, because you have to always choose those W1 and W2, but you can, if you just can always start with just a positive definite function, which is time invariant. So let's say we start with our standard half x squared, right? And this half x squared is always, there's always a upper bound and lower bound, which is equal to half x squared. So that, remember that less than equal to is there, so you can always say that half square upper and lower, because it's a time invariant system. It is equal to its lower and upper bound, so not a problem. So so what will be v dot x? v dot x will be x into x dot, which is minus x4 1 plus gt, right? So that now v dot came out to be time dependent. Now v dot is this v dot, but what we have to show that if it is less than equal to some minus w3x, right? Yeah, if we can show that there exists another, so in that case, if I say, let's say if gt equals to 0, means what I'm trying to do is take an upper bound on this or lower bound on this, right? Because I'm saying negative. So if I take this gt equals to 0, then it will be less than equal to minus x4, right? Can I say that? That minus x4 1 plus gt is always less than equal to minus x4. Is it possible to say that? Right? So see, if you break it down, it is minus x4 into gt, right? Correct? And as I said, gt is always either greater than 0 or equal to 0, right? So that means this quantity, overall quantity, will always be less than minus x4, right? Because this adds to more negativeness, right? So that means this is our w3x. So if you see your theorem in the previous next page, negative x4, it's always negative. Negative x4 is always negative, and this quantity is always less than this quantity. So you have to just come up, you have to show that this quantity here, v dot t, is always less than equal to the time invariant negative definite function. So then this is a uniformly asymptotically stable system, right? So that's the idea. You basically take a lowest bound of this quantity, right? Lowest bound will become when I make gt to be 0. Because lowest of negative is always less than, anything you add will become less than this quantity, right? So got it? So let's see if one more example can be done. Example. So this time it is x1 dot equals to minus x1 minus gt of x2, and x2 dot equals to x1 minus x2, where g is continuous and gt is given to you between 0 to k. So you don't exactly know what gt is, but they are saying gt is bounded below by 0 and above by k. So you know the maximum invariant, you don't exactly know what gt is, but all you know is this property of gt. Okay? Got it? So now what we will do? So let's say our Lyapunov candidate function this time, this time we can choose, let's say vtx is x1 squared plus 1 plus gt of x squared. Let's say I choose this quantity. This time I have a time varying Lyapunov candidate function. So if you go back to your theorem, right, so that I can do, I can say this quantity is less than equal to, if I make gt 0 for the first time, for getting the lower bound, it will be x1 square plus x2 square, right? So that's true, right? 1 plus gt will always be greater than equal to this quantity depending on what values gt takes between 0 and k. An upper bound can be simply chosen to be x. We are not using this property anywhere, but we are just ensuring that there is upper and lower bound by k functions, class k functions, right? So this will be x1 square plus 1 plus k. We can choose the largest value here. So 1 plus k x2 square, right? So that's w1 That's W2, right? So you have, it is upper and lower bounded by a time invariant positive definite functions. That's the idea here. Now, let's find V dot. So V dot is again del V by del T plus del V by del X transpose into F dot X, FTX, right? That's your, so what will be that? Del V by del T will be, did I say it is continuously differentiable? This is already, this is also given. One more thing is given.
G dot is equal to
G dot T
Less than.
is less than equal to G of T. So this quantity is given. So from here, if I take differentiation of V, so it will be G dot T x2 squared, right? And then we go about doing x1 dot plus x2 oh, so 2 should be there, right? 2 x2 dot into 1 plus gt, right? So now if we go ahead and plug things in, so let's keep it G dot T right now here, because this will be used for the getting the lower upper bound thing. What is x1 dot? X1 dot is minus x1 gt, so it will be minus 2 x1 squared minus 2 gt x1 x2, and then let's compute this. This will be 2x2, so minus 2x1 x2 minus 2x2 squared whole thing multiplied by 1 plus gt, right? So that's the thing. Let's see, things will cancel out, right? So let's again open this up. G dot T into x2 squared minus 2x1 squared minus 2gt x1 x2. Let's open this up. So 2x1, so it is plus 2x1 x2 2x1 x2, and you have plus 2x1 x2 gt, right? And minus 2x2 squared minus 2x2 squared of gt. I don't know if I have opened too much, but I think I can cancel this out here at least, right? So now I can collect terms, like I have x2 squared terms here and here, I have x1 squared terms here and here, more x2 terms, right? So then all this jazz. Did I do something wrong? Was it cancelling?
So V dot ultimately equals negative 2x1 squared plus 2x1 x2.
So V dot is ultimately, what is that?
Negative 2x1 squared
Okay.
plus 2x1 x2
Plus 2x1 x2. Yes.
minus the quantity.
Mm-hmm.
You got 2 plus 2gt
Oh,
minus g dot squared.
okay, I got it. So
All times the quantity
2
x2
1
squared.
minus g. So this is 2 1 minus g x1 x2, right? That's the
not
fine.
quite here. Minus 2 times that quantity. You got the 2 plus 2gt minus. There's no 2 there.
I got it.
Times the quantity x2 squared.
So the final expression came out to be 2x1 squared plus 2x1 x2. That's true. This is there. And then you see x2 square is here, x2 square is here. So you can,
Right.
so basically you can take out that common. Right. So I think we were doing correct. So then it came out to be 2 plus 2g minus g dot
times
x2 squared.
Yes.
Right. So that's what we got. Interesting. So now if you see this I don't know if have you seen this forms before? Yes, right? For example, just let me write something like minus 2x1 squared minus 2x2 squared and 2x1 x2 can be represented as a positive definite matrix multiplied by x1 x2, right? No? Yes?
Multiplied by.
So if I have a matrix like 1 0 0 1 and I have this x transpose x, what is this? This is x1 square plus x2 squared, right? I can write this matrix. Similarly, this matrix can be written as a matrix form, right? Right? So now what we are saying is, what is g dot? What was g dot is less than. So let's start putting bounds on this now. So v dot is less than equal to, I would say if g dot is less than g, right? That's what it was told, right? So your g dot is somewhere g dot t is less than equal to gt. So since we are using less than equal to here, we can say this is equal to g, so that subtraction will make this g, right? So I can write it minus 2x1 squared plus 2x1 x2 minus 2 plus g Can I get the book again? Just want to see. Okay, so basically all we are stuck is here. This is time varying thing, right? Everything is time invariant. So remember, we have to show that this is less than equal to some minus omega 3x, right? So if I can put a lower bound on this, what is the lowest so maximum bound, sorry. So this quantity is less than what quantity? So if you go, what is 0? So you're actually lowest bound, because it's a negative sign, right? So g is between 0 and k.
Alright, so 2.
So it should be 2, right? So this whole quantity 2 plus 2 g minus g dot is less than equal to 2, right? So I can use 2 there. So this quantity is less than equal to minus 2x1 square plus 2x1 x2 minus 2x2 squared, right? So this is, if you see, now we don't know whether it is positive definite or not, but you can write this as x transpose into 2 minus 1 minus 1 2 into x. This whole thing, this whole multiplication can be written like this, basically, which is equal to minus x transpose minus, minus, if we take minus outside, yeah, it should be minus here, right? So 2 minus 1 minus 1. So it's 2 minus 1 2 minus 1 2 into x transpose. So this is a positive definite matrix, and therefore this whole multiplication is always negative. So now what does it say? We have shown that v dot is less than a negative definite quantity, in time invariant negative definite quantity. So that means it is uniformly asymptotically stable. Okay.
So
quantity is less than G, where exactly did we calculate that?
So you can use
Oh, it's given.
That's when we went back and added to it.
so you can always say that this is just 2 plus G kind of thing, right? Less than equal to, and then G you can say this quantity is less, the lowest bound on this will be 2. So this is always greater than 2, right? So okay, got it? What time is it?
2.
2. And our class is still?
2.
No. 2.
2:30ish. Yeah.
2:20, right? So we have 20 minutes, right? So, well, let me put the battery on it. So that's another trick. So next topic is pretty interesting. If you see, so it's called input to state stability. Can
Chapter 5.
is that chapter 5 or?
Oh, maybe I'm right. Okay.
So in this,
Chapter 5 was input output.
so we have input to state stability, and then I think in chapter 5 we'll have some boundedness conditions. So yeah, don't just stick with me and we'll. So why it is important? Once about.
Yeah, chapter 5 says input output stability.
Mhm.
But we're still in chapter 4, which also says input to state
Yeah.
stability.
So
Okay.
let's do input to state stability first.
Okay.
Input to state stability. I don't know if you remember the Bibo stability principles. What was it? Bounded input, bounded output. Till now, what are we doing? We are saying that we have x dot equals to f of x or f of tx, right?
You were looking at internal stability.
So these are all internal Lyapunov type stabilities where we say, hey, you start at initial condition, whether what happens to your trajectories, they are bounded or they go to origin, whatever. But right, so origin is what we are saying, whether it is attracting or repelling. But in input to state stability, we will deal with systems where you have u, and because of u, the x equals to 0 is no more your, what to say, an equilibrium point. And now, even if it is not an equilibrium point, we want to find out how close you can get to an equilibrium point kind of thing. Or basically, if you apply a bounded input, your system is bounded or not. Okay? So that's the idea here. So now we are dealing with systems of this nature, f of t x u. So whatever you did till now will be useful here, because first thing will be to compute what is the nature of the trajectory with u equals to 0. When the u equals to 0, all the previous analysis applies. Here you first find out what is happening there, and then we'll go from further. Okay, so f is defined again on all that awesome stuff. F is defined on 0 to infinity. D, now this time also dn. So you have a third input also, right? Because u is there, which is giving you r, and f is piecewise continuous and locally Lipschitz. Again, local Lipschitzness is again our kind of in x and u, and your dn is open, connected, and contains u equals to 0. So we are defining this dn, nature of this space for u. What what variables or what values your u can take, right? So your u of t is continuous, bounded function of t. If it is a function of x, then it again converts to the same autonomous problem where you can just say x. So this is just a function of t for all greater than t. Something like u equals to a sine t, right? It's bounded, it's a function of time, it's continuous, right? So so let's do the math. So assume that your x dot equals to f of t x 0, means with no input. Make your u equals to 0 with no input. It is UAS. What is UAS? Uniformly asymptotically stable, right? So if that's the case, then you can rewrite the equation, right? The top equation can be written as f x dot equal, you can add and subtract this to the top equation, right? This equation, add this plus this minus this, so basically you're adding in 0. So I can say my x dot is equal to f of t comma x comma 0 plus your original f of t comma x comma u minus f of t comma x comma 0. You can write this, right? So you have this additional term here. Now remember, this is like doing the Lipschitz condition testing, right? Remember? Now you're going from one place, like t and s x remains same, but you're saying compute at u non equal to 0 and u equals to 0. So this f can be like that Lipschitz difference, and we said that it is Lipschitz for x and u. It is locally Lipschitz for x and u, right? Locally Lipschitz for x and u, right? So that means we can use that property here, some property here, because this will be bounded, right? If it is locally Lipschitz in a domain. So that's what I want to show that. So now this is a solution of two things, right? One is the solution at 0, like having your origin asymptotically stable plus some bounded nuisance because u is added to it. So because it is locally Lipschitz, I can write this again here as f of t comma x comma u minus f of t comma x comma 0 as something like L of u, right? You remember Lipschitz conditions like f of x minus f of y is less than equal to L of x. Remember? So that's what I'm applying. In this time I'm doing in terms of u. So, right? Nothing. So now there are two parts to it, right? One part is the solution of this equation, and one part is because of this here, right? So what is the solution when it is uniformly asymptotically stable? We have already assumed, we started with that assumption, right? That it is uniformly asymptotically stable without input. So we are saying original system is uniformly asymptotically stable, and suddenly some external disturbance comes or somebody applies some input. What is the nature of the solution? So, and then we can write this, right? Then if you remember, the solution of this can be written as a KL, type KL solution, right? If you remember. So let me write it. So you will see that x of t now can be written. If you ignore this part for now, ignore it and write the solution for this f of tx, and we know that it is uniformly asymptotically stable. That means x of t is less than equal to some beta, some KL function x of t0, right? T comma t0, right? T minus t0 means this quantity is going to as t minus 0 goes to infinity, this quantity goes to 0. Because we know we started with that assumption. Plus some function of this L of u. Some additional term, because it's going to 0, but now we have this L of u because of this. This whole quantity is, so that will be rho L into maximum, if you see, supremum, but tau greater than t0, u tau d tau. So basically you integrate this part, right? Because it is x dot, if this part is constant, if you want to integrate, it will be just 0 to tau d tau, right? So you can say whatever that u is, you take the maximum, because we are finding the maximum bound here. You can use this. Let me rewrite this. It's rho of L. Supremum means the maximum, because u can be we are talking about uniform u tau d tau. Okay, so now this is the solution. Right? This will, and we don't know what is happening. Like, we know that this quantity goes to 0, but if we can show that this also is bounded, then it is input to state stable, right? Right now we don't know what happens when I integrate this u of tau to d tau. I don't know if you remember your bounded input, bounded output stability. That whole g of tau, if we integrate it, should be less than infinity. That is the bounded definition. And when do you think a curve will be less than infinity? If it is going down, right?
Oh, okay.
If any curve that you integrate, if it is not of this nature, it is always going to be unbounded. Only this type of curve, when you integrate, even the constant term, if you integrate, it will go to infinity, other than 0, of course. Right? So you get this. So we have to show that if this u tau d tau, what happens to that? Okay, so let's go there. So some definitions now. So I'm just giving you the solution here, that this is how the solution should look like. But now we can give some definitions here. So x dot of f of t x u is locally, we are doing input to state stability, right? Locally input to state stable if there exists this beta which belongs to KL and gamma which belongs to class K function, and constants K1 greater than 0, K2 greater than 0, such that for all x of t0 less than K1, and so what I'm saying is your initial condition is bounded, of course, right? So it's finite, less than K1, and your supremum of t greater than t0 is ut less than K2. So, right? So your u is bounded below by K. Then your x of t can be written, just rewriting the above part, which is beta of x t0 comma t minus t0 plus gamma supremum of t0 less than equal to tau less than equal to t u tau d tau. Okay. For all 0 t0 to t, between 0 to t. Then your system is input to state stable. Like okay. The system is input to state. I think it will be more clear when we take an example. So many wordings came here. Is there an example there?
Probably.
So this is just a definition that if a input to state stable system means this, the solution should look like this. Okay, and we should be able to show that the main important part, because this is pretty clear, right? This is pretty clear that if system is asymptotically stable without the input, then we have one part of the solution is this. So that's pretty clear. The question is, how do we find this gamma? Right? This is which is class K function of U. How do we find that? Is what the main important thing is. So that next Lyapunov theorem basically connects everything. So that will tell you exactly how to find that gamma. Okay. So let's see if we want to give the theorem first, or I want to do the proof first. Anyways, let me give the theorem, and then things will be clear. Let me take. Sorry. This gamma is what we are dealing with, right? What is that gamma? What will be the bound for x? Because this quantity goes to 0, then you will be remaining, the x of t will be less than this particular bound, that gamma bound, right? So we are basically, this theorem is doing two things. It is telling that it is input to state stable. Also, it is telling what will be the ultimate bound on x. That's very good, because you can now tell, doesn't matter, I don't have an equilibrium point, but I can go close to 0 to the origin with this bound, and that bound, okay. So this theorem tells you, theorem 14, and you will see how things are connected, 4.19. So we have, let's say, alpha 1 x. So v of tx alpha 2 x. So remember, we should be able to upper and lower bound Lyapunov candidate function by class K functions, right? If you just initially in the beginning we said that any positive definite function can be, like for lambda max of x is a class K function, right? Lambda min of x norm is a class K function. Then let's say your del v by del t plus, so basically your v dot del v by del x transpose into f of t comma xu is less than equal to minus w3. Okay, x. If this was true, then there was no problem. we know that this is true for u equals to 0. But when that u not equals to 0 comes in, this will only be true for a certain condition for x. That if x is greater than this quantity, then this is true. It will be clear from example. So w of 3x is greater for all x is greater than equal to rho of u greater than 0. Okay? So we are saying that this condition is now violated because u is not 0. It was, of course, you could find it is. Now you will see that it will only be true if your x is greater than some function of u. Like let's say mod of x is greater than 2 of mod of u or whatever that is. You will see when we take the example, it will be much clearer. So first thing we'll be finding out this x, like what is that x? What is that boundary for which this condition is true? So what happens? Let's say this boundary, right? We are saying that if x is greater than this, then it is always, it satisfies this quantity, which is negatively definite, right? Which means I'm attracted towards this. And once you enter, so in this quantity here I don't know what happens, but outside I can guarantee that this is negative. So this basically becomes the, you can say that system will come eventually to this boundary, which is so we will also be able to find the bounds, because of that, even if there is non-zero u, and because of that equilibrium is disturbed now, you will be able to tell how close I can get to the boundary. Because what I'm saying is this condition is true if x is greater than some function of u. Okay.
And rho is just any.
Rho is just any function, something like 2 of u or u square, or we'll get rho is just it's a class K function. Rho is a class K function. Okay. So
changing u will just change the bound.
Yeah, changes in u will change the bound. So let's so where alpha 1 and alpha 2 are class K infinity, rho is class K, and w3x is continuous positive definite. Okay, and so you can say, like final statement can be, this is input to state stable with gamma. If you remember, our solution had a gamma into it somewhere in the previous page. Found using where gamma is equals to alpha 1 inverse 0 of alpha 2, a function of rho. So 3 functions together. So rho plugged in alpha 2 and alpha 2 plugged in alpha n1 inverse will make a gamma. And you can see, if you remember the properties, this will be a class K function. This will be a class K function as well. And if you see the proof, it's very the proof is very simple. But let's take an example. Things will be very clear after that. Okay. So very quickly an example. X dot equals to minus x cube plus u. As simple as that. Okay. So without u, first step is to show that without u, when u equals to, what happens when u equals to 0? X dot equals to minus x cube, and if we choose v equals to half x squared, v dot is x dot x dot, which is equal to minus x4, which is negative definite, less than 0. That means it's uniformly asymptotically stable, or asymptotically stable, as uniform is not needed because it's not time varying. Done, right? Time t equals to 0. With u equals to 0, it is asymptotically stable. Okay? In fact, globally asymptotically stable, because this is radially unbounded, right? So now let's plug u in and see what happens to the same v dot, right? So when we plug u in, So same Lyapunov candidate function. Now v dot equals to x dot, and now v dot becomes, things will be very clear after this example. You'll see that theorem will make sense. So now we do x dot is minus x4 plus xu. Right? What happened after this guy is messing up? Right? We cannot say now. Can we say, now we have to come up with some x, that what conditions on x should be satisfied such that this quantity is negative definite. Okay? So to do that, we do it, apply it, we say that, let's say we can break this down, this x4 into two parts. Right? One is, let's say, what I can say is, let's say 1 minus theta x4. Theta can be anything between 0 to 1 plus, so minus theta x4 plus xu, right? Nothing added, 0 only. Theta x4 and theta x4 when you add is a 0. But now you're separated out that, okay, let's take some portion of x4 out and show that. So when we do that, what can I say? So theta is between 0 and 1. Okay? Some quantity, 0.8, 0.9, 0.7, anything. So this quantity will always stay negative, right? Whatever theta value is. Right? So when can we say that, so what we can say is, now this is negative, but now we have to show that this, when will this be negative? Right? So if this can also be said, this quantity is at least, so for that I can say that, minus theta x4 plus xu is less than equal to 0. Right? If I solve, now see, I'm trying to solve for x now, that what x, right? If I apply, because this is already taken care of, this is negative, and now I'm saying that if we can show that at least for what values of x this will be less than equal to 0, then the whole quantity will be negative, right? So we are saying for what values of x, this is always negative, doesn't matter what x is. Now I'm just trying to see what quantity of what should be x such that this quantity is less than 0 or equal to 0. Equal to 0 will also help you, because then this is negative, right? So our game. So if you do that, then we can solve, like if you take the mod of it, it will be basically saying mod of x4 greater, so when negative sign goes, that side becomes less xx mod of, so you can do this, right? Minus x4 less greater than equal, x4 greater than equal to xu. You can take mod both sides, it will be xx will cancel out, and mod of x cube less than equal to mod of u.
Theta.
Oh, and theta, sorry. Where is theta?
You missed the theta.
Yeah, theta part also was there, right? So theta. Theta is always positive, so it doesn't matter to it, right? So this quantity. So x of cube greater than equal to mu mod of mu over theta. Basically x of greater than equal to mu over theta 1/3. So what I'm saying, when x is greater than this function of u, then that quantity is less than equal to 0. What it is showing? I'm showing that it is negative definite guaranteed if your x is greater than this number. Function of u.
Can you scroll up? What was the point of introducing theta? You could have done that without.
Yeah.
Okay.
It's theta kind of separates it out.
You
That,
could have
okay.
done that just using this, right?
Yeah, we could have.
Well,
now how would you like?
hold on.
Yeah, I want to
Scroll
show
down.
that there is. I want to show that this thing, right, this is made up of some minus W3x plus something less than equal to
Okay,
0.
that's
So,
what you
so
want
that
to do
means
now.
I need a negative definite part to be assured, guaranteed. So that theta you can choose to be very small value. That, you know, even the smallest value of this is. So what I'm saying, when x is greater than this quantity, we are negative definite. Okay, that means it is input to state stable because now you got that value, right? You can also compute your gamma now, right? So if you remember, what was your gamma? Your gamma was alpha. Where is that? Alpha 1 inverse of alpha 2 of rho. So this is rho, if you remember. I said when, right? So this is rho. So alpha 1 and alpha 2 are same because we have a very simple, so they are just unities. So they will cancel out. So basically gamma will be your rho. So your x, if you remember, your x will be your x will be, yeah, so then gamma will be just so gamma, so if you just put r into x into this quantity, right, so alpha 2 rho. So alpha 1, alpha 2 cancels out, and then this is, so yeah, that's gamma, right? So instead of u, you can put mod of x to it. So your x or r to it. So some r by theta 1 by 3. Your x will be bounded by this radius. So that's ultimate bound, because outside this circle, you are always negative definite. So come in.
So we started with that inequality, right? X4 cross xy is less than 0 and
XU, yeah.
Yeah, that implies that result. But I
Yeah.
wonder if that the modulus of x, if that inequality is satisfied, does it apply above expression also?
Which above expression you are talking about?
So if we started here and
Yeah.
showed this, but if this is correct, then does it
Yes,
imply this is
yes,
correct?
yes,
So
yes. That's how we got it, right? If you put that in, you can multiply things and check out actually. Yep. Yep.
So the converse to the
Yeah, if x is greater than that quantity, that mu by theta, this mu 1 by, if for this x, this is always true. Because that's how we computed it, right? That it has to be true. So if x is greater than some function of u, which ensures that we have a negative definiteness in v dot, then we don't have to, we will not go to the origin, but we can show that we are bounded. We will get close to origin, and this is how close we will get to the origin. Very important. Means of course the math will always get tricky. It will not be that simple, because getting that ultimate bound, you will have to take function inverses and all that stuff. But that's how we will deal with it. Okay, there are a couple of examples that we will do in the next class. But I think after this, we are going to sliding mode control, because now we have all the tools in toolbox after this input to state stability and ultimate boundedness. Like this is how you compute your boundedness also. Like in chapter 5 is about finding boundedness, but I think they are using this input to state stability concept. Like, that gives you the boundedness. And you should be ready to dig in. So from chapter 4, we will directly jump into chapter 14. Do some couple of problems, inverted pendulum to start with. Sliding mode control is a very interesting problem. Like, for example, you have some uncertainty, like you don't know some functions. you can still slide to origin. Even in the presence of slide to origin means you can become. So you make a slope, right? That's the slope. So you don't know what functions are, but somehow if you can take the trajectory to this slope, you will slide to the origin. So that's the whole idea of sliding mode control. So you force your system to go into this slide, and then it slides down. You guarantee even in the absence of uncertainty or whatever in your functions, you will slide down to the origin. So that will be interesting to see. Okay. So Friday we should be able to do some of this and then a couple of examples of this and then do some homework problems. Okay. Is it time now?
It's been time.